This lecture is part of an undergraduate course on complex analysis and will be about analytic continuation. So analytic continuation is one of the most extraordinary properties of holomorphic functions. In fact, it's so bizarre that when I first heard it, I thought it was obviously wrong and I thought I must have misunderstood. So what it says is the following. Suppose we've got some sort of open set U, which is connected, and suppose we've got a holomorphic function f on U, and then if you know f on some very tiny little circle here, so it might be some little circle the size of an atom or something like that, then f is determined everywhere else, even if you're sort of light years away. So the point here might be Alpha Centauri or somewhere like that, and the values of f way over here are still determined by its values on this tiny little circle. Notice that for real functions on the real line, the analogue of this for smooth functions is completely false. For example, if you take f of x is 0 for x less than or equal to 0, and e to the minus 1 over x squared for x greater than 0, the function looks something like this. So here it's 0, and here it's not 0, and this function is infinitely differentiable, but its values here are just 0, and obviously knowing that it's 0 here doesn't allow you to deduce that it's 1 there. I mean, it might just be 0. So the key point of the proof is that if f is holomorphic on U, so you remember U is connected and open, and if f is not identically 0, then the zeros of f are discrete in U, and that means that there are no limit points in the set U. It can have limit points outside U. For example, if we take f of z is sine of 1 over z, and we take U to be the complex numbers minus the origin, then if you look at the zeros of f, they look something like this. The zeros of f have 0 as limit points, but this limit point is not in the set U, so that's okay, that's allowed. Proving this is quite easy. All we have to do is to use the idea that holomorphic functions can be expanded as power series. So suppose 0 is a limit point of zeros of f, and we're going to take 0 to be in U, so we're just assuming that the limit point is 0 to make notation a little bit easier. Then f is equal to 0 near 0. That means f vanishes in a small neighbourhood of 0. Well, otherwise we can expand f as a power series. So it's a n z to the n plus a n plus 1 z to the n plus 1 and so on, where some coefficient is not equal to 0. So we will focus on the smallest non-zero coefficient. If there isn't a non-zero coefficient, then f is 0 near 0 because it's holomorphic. And now we can write this as z to the n times a n plus 1 z and so on. And now we notice that this is a continuous function, and it's not 0 at z equals 0 because a n is non-zero, so it's not 0 near z equals 0, because if a continuous function doesn't vanish at 0, then it doesn't vanish in some neighbourhood at 0. But this contradicts our assumption that 0 is a limit point of zeros of f. So any limit point of 0, if we've got a limit point of zeros of f, then f must actually vanish in some neighbourhood of that point. Now we can finish it off easily. So we just let v be the largest open subset of U with f equals 0 on V. And now we notice that V is closed under taking limits by the previous sheet. Well, I guess it's not above, but whatever. Because if anything is a limit point of V, then it's a limit point of zeros. So by the previous result, f must actually vanish in a neighbourhood of that. And we also notice that V is non-empty, because we assumed that some point was a limit point of zeros of f, and so f must vanish in a neighbourhood of that point. So V is closed, open. This implies V is equal to the empty set or U, as U is connected. This is where we use the assumption that U is connected. And as we've just pointed out that V is non-empty, this can't hold. So V must actually be U. So f is identically 0, which is no good because we assumed f wasn't identically 0. So this shows that the zeros of f in U form a discrete set unless U is identically 0. Now let's prove analytic continuation. So suppose f is equal to G on some set S with a limit point in U. So this is the key assumption on S. So here's U, and here's our set S, and we're assuming that f is equal to G on this set here. Then f minus G is equal to 0 on on the set S. So f is minus G is equal to 0. Otherwise, we get a holomorphic, a non-zero holomorphic function with zeros having a limit point in U, which contradicts our previous result. So f must actually be equal to G. So if two functions are equal on some set having a limit point in U, they must be equal everywhere. Again, we're assuming U is open and connected and f and g are holomorphic, of course. In particular, if f and g are equal on a small open set, well, there are obviously limit points of that open set in U, as long as the open set is non-empty. By the way, you can ask if there's a converse to this, that if we've got a collection of points with no limit set in U, can we find a function that vanishes exactly on those points? And the answer turns out to be yes, but that might come later in the course. I said this is a result that holds for complex differentiable functions, but totally fails for real differentiable functions. There is an analogue for real functions, provided you use analytic real functions. So what does analytic mean? Well, analytic just means it can be expanded as a power series near each point. So we're not claiming that there's a power series that works for the whole function, but we're saying that for each point there's a power series that works near that function. And you notice the only property of holomorphic functions we used was that it could be expanded as a power series at each point. So for real functions with this property, we can also prove analytic continuation. So we've got this big difference between smooth functions, which have an infinite number of derivatives and analytic functions, which can be expanded in a power series. And the point is that smooth functions are kind of floppy in some sense. If you know a smooth function somewhere, it doesn't really tell you anything at all about its values anywhere else. Whereas analytic functions are very rigid. Once you know the function somewhere, that completely determines it everywhere else. And if you alter the function on some point, then that forces it to change everywhere else. So complex analysis is very much about holomorphic functions, which are always analytic, whereas real analysis tends to be mostly about smooth or differentiable functions, which are floppy. Although, of course, you can do real analysis with analytic functions. So this gives the property of analytic continuation, which is just a special case of this. Suppose we've got a function f is holomorphic on some open non-empty set V, and suppose we've got some bigger set U that is connected. Then we see that if we know f on V, there's at most one way to extend f to U. And you can ask, is there at least one way? And the answer turns out to be sometimes there is and sometimes there isn't. For instance, if f is the function 1 over z and V is some open subset of the complex plane, you can't extend it to the whole of the complex plane because at the origin it's going to be infinite. But in practice we can very often extend it. And if we can extend it, this is called an analytic continuation. And this is a very magical property because quite often the analytic continuation contains some very interesting extra information about the function which you didn't see from its original definition. So I'm going to give a couple of examples of this. So the first example is the gamma function. So gamma of s is defined to be the integral from 0 to infinity of e to the minus t to the s minus 1 dt, as Euler came up with. And the interesting thing about the gamma function is it's an extension of the factorial function to real numbers, because we see that gamma of s plus 1 is equal to gamma of s times s. And you can see that by integration by parts. You differentiate this bit and integrate that bit, and a very easy argument proves this. So in particular, this shows that gamma of n plus 1 is equal to n factorial when n is equal to 0, 1, 2. Why we put the plus 1 there is a sort of historical accident that annoys everybody. We can also define it for complex variable s, and it's fairly easy to check the integral converges for s for the real part of s being greater than 0. So we get a sort of picture like this. So here's the point 0, and the integral converges in this region here. So we can also check that it's holomorphic in this region. And in order to check it's holomorphic, we need to be able to differentiate under the integral sign. So how can we differentiate under the integral sign? Well, first of all, this function here is very nice and differentiable, so that's one of the conditions we need for differentiating it under the integral sign. The integral is derivative. The other condition we had was that we should integrate over a finite interval. Well, if you look at this, we see that this isn't actually a finite interval, so that doesn't quite apply. But the function is very rapidly decreasing on this interval, so that's nearly as good as the interval being finite. So we want the integrand e to the minus t to the s minus 1 has continuous derivative and is rapidly decreasing. Maybe its derivatives are rapidly decreasing as well. So we've got this gamma function defined in some open region, and the question is, can we extend it to an analytic function in a bigger open region? And the answer is yes, because we can put gamma of s equals gamma of s plus 1 over s. And we can use this to define gamma s for the real part of s is greater than -1, except for s being equal to 0, because if the real part of s is greater than -1, this bit's holomorphic, and this bit is holomorphic except at s equals 0. So what we've done is we started with gamma s in this region here, and we've managed to extend it to a slightly bigger region here, except for this point. And now we can repeat this trick again. We can now use this to define for real part of s greater than -2, because if the real part of s is greater than -2, then s plus 1 has real part greater than or equal to -1, except we run into another problem, because if s is -1 or 0, then we again run into a problem. So we can extend it to an even bigger region like this. And we can obviously keep repeating this, and what we find is that gamma of s is holomorphic for all s except s equals 0, -1, -2, and so on. Of course, strictly speaking, this is a different function from gamma of s because we've defined it in a bigger domain, but the convention is you just call, if you analytically continue a function, you generally say it's the same function, although a really pedantic set theorist might object to this. So the next example shows we've got to be a little bit careful. Suppose we take the function log of z, which we can certainly define for the real part of z greater than 0, say. So we know log of z is a bit funny over the whole plane, but we can certainly define it in this region here, just by saying the, you remember, to define log of z, we need to choose the argument, and we can easily define the argument of a complex number in this region. And now we can analytically continue it to -1 in two ways. First of all, we could extend it in this green region, and if we extend it in this green region, we find the log of -1 is equal to pi I, but we can also extend log of z. If we ignore the green region, we can extend it to this orange region, and in the orange region we find that log of -1 is equal to -pi I. So analytic continuation, we've got to be a little bit careful. We can get several different answers for the analytic continuation of a function, depending on which region we analytically continue it into. Of course, we can't analytically continue it simultaneously into both the green and the orange region, because we would then get a contradiction. So when you say the analytic continuation of a function is unique, that means it's unique once you've determined the exact region U you're analytically continuing it into. It may depend on the region U. So finally, we'll look at the analytic continuation of the Riemann zeta function, which is 1 over 1 to the s plus 1 over 2 to the s plus 1 over 3 to the s, and so on. So you remember the Riemann hypothesis talks about the zeros of this with real part at half, and the problem is this doesn't actually converge if the real part is at half, so it converges for the real part of s is greater than 1. So here we have the point 0 and 1, and it converges in this region here. And what we really want to know are the values of zeta on this line here. So how can we extend it? Well, first of all, we want to know that zeta of s is holomorphic in this region. And this requires a theorem on when sums of series are holomorphic functions. And we're going to postpone this until next lecture. So we'll just assume for the moment that this is holomorphic. So how can we extend it? Well, what we can do is we can write 1 over 2 to the s times zeta of s is going to be 1 over 2 to the s plus 1 over 4 to the s plus 1 over 6 to the s, and so on. That's rather obvious. And now if we take this series and subtract twice this series, so we take zeta of s minus 2 over 2 to the s zeta of s, we're going to get 1 over 1 to the s minus 1 over 2 to the s plus 1 over 3 to the s, and so on. And now you can see this actually converges for s equals 1 because it's just an alternating series. In fact, we can check this converges for the real part of s is greater than 0. And again, this is a slightly tricky convergence problem that we will talk about next lecture. And it converges to a holomorphic function in this region, which again is something we will discuss next lecture when we talk about when a sum of holomorphic functions is holomorphic. So we can use this formula when we've checked that this is actually holomorphic to define zeta of s, because we can write zeta of s is equal to 1 over 1 minus 2 over 2 to the s times this series here, 1 over 1 to the s minus 1 over 2 to the s, and so on. And this bit is holomorphic, and this bit is holomorphic as long as this function is non-zero, which it has a few zeros on the when s is real part 1, but otherwise it's holomorphic. So this defines zeta of s on the so-called critical line where the real part of s is equal to a half, and this means it actually makes sense to talk about whether the zeta function has zeros with real part equal to a half or not. So the Riemann hypothesis does actually make sense. Okay, well, there are several problems left to talk about. First of all, we need to talk about when this converges, and secondly, we need to talk about whether it's a holomorphic function when it converges. And as I said, we're going to do all that next lecture, where we discuss the problem of when a series of holomorphic functions has a holomorphic sum.